Recording in progress.
Puedo empezar.
Maybe we should start again.
Okay. Nice. If you miss something, nice. Okay. So well, I'm happy to be here. Let's go to the presentation. So first of all, why if you are here is because you care about complex systems, and we know that there are many tools like dynamical systems, information theory, stochastic processes. But here we want to use a new tool which has been broadly applied to many systems, but of physical interpretation in the sense that you can define an energy function or heat function. And the quest of this master thesis is how can we extend this framework to broader systems such as social systems or an economic system, you name it, more general complex systems. There are already studies in this direction. And what are we going to do that is new from them? So first of all, we're going to introduce a new model which has rich features and also is more adequate for stochastic thermodynamic analysis, as we will see. Secondly, our model serves as a counterexample of certain theoretical misconception of the previous papers. And also, we emphasize that we're going to do a mathematical approach. We don't want to rely on the thermodynamical interpretation, as other papers have already done. And on the way, we will find some of the most beautiful equations that I have seen, so I hope you enjoy it. So what are we going to do? For a matter of time, I will go straight to the model. I will define it. I will give the rates of the model, and then I will jump to the results. And I will discuss the equilibrium state, the stationary states, which by now maybe some of you are wondering what is the difference between them. I will stress that deeply. Then stochastic thermodynamics provides us with two ways of looking at the system. One is the ensemble, or the average one, which is the common in statistical physics and thermodynamics. And the other one is a path description in terms of the realization of the stochastic process. So we will do the analysis on both of them. We will also do the conclusions and the future directions. So what is our model? So we consider an agents which have two different states, red or blue. And this is a binary state system. And we consider an all-to-all interaction to make things easier. And therefore, we can use the macroscopic description of the stochastic process. Then, as in any social system, you need to define some social mechanisms for which we introduce a parameter, the nonlinear parameter, which is Q, which accounts, which will be accounts for the interaction, the grouping interaction that we will take into account. First, we consider herding, for which you have an agent. Here I set Q equal to 3 for illustrative purposes, and interacts with another agent. Then it interacts with another, and then we allow repetition. It can interact with the same and changes its state with certain probability. This is the first mechanism that we consider, and it can be represented as these reaction rates. And further, we consider an idiosyncratic mechanism in which you have the agent interacts with an agent J, an agent K, an agent L, and then it changes its opinion. There are sociological theories that motivate this, but there are also models that have these kind of mechanisms in the literature. So we are backed up by them. And this can be represented by these reactions. But for doing a proper analysis of stochastic thermodynamics, we want our system to not generate irreversibility from its definition. And for this, we will consider the coupled reaction case. So this will be our model. In particular, we will concentrate on the symmetric case, which is the case in which you consider all the parameters equal. Notice that our model includes the Q-voter model and the voter model as particular cases. And now, why this model and not another, if there are so many models in the literature? So first of all, it is simple, which is always nice for exploratory analysis, as we are doing. Second, it lacks of the thermodynamic interpretation. What does energy mean here? It doesn't have any sense. Secondly, it is microscopically, the four features that I'm going to mention now are motivated by the stochastic thermodynamics formalism, and I will discuss them later in greater detail. But basically, it is microscopically reversible and satisfies local and global detail balance and provides a natural separation of the rates. So the model, the stochastic thermodynamics formalisms ask us to separate the sources. For this, we consider our system with our macroscopic description, and we attach a reservoir, which is given by reaction 1, and these are the rates. And we attach another reservoir, which is given by reaction 2. The usual global rates that you consider in stochastic processes is the sum of the two rates given by each of the reservoirs. And we consider these currents, which are not heat currents, but probability currents here, okay, defined in this way. So our model is microscopically reversible, which means that for any allowed jump, the reverse jump is also allowed. Then stochastic thermodynamics provides us a way to properly define equilibrium states. That is, when there are no macroscopic currents, so the currents of the reservoirs are equal to 0, which is different from the stationary state in which the sum of all the macroscopic currents are 0. The net current is 0. It also satisfies detail balance, which is given by this condition. It's very important for our analysis, and global detail balance, which is given by the, so here, let me explain. So here we are considering only one of the reservoirs, the reservoir nu. We remove the other one, and the system reaches the equilibrium distribution. And in the other case, we consider the full system, and we reach the stationary distribution. There's a proposition that shows that our model does satisfy these properties. And further, it is interesting to note that there are some restrictions in our model. Firstly, obviously, we bound the jumps in the domain of the possible states. And secondly, and more interestingly, we have isolated states. If we consider the submodel of one reservoir with the system, for example, reservoir 1, you can, if you are at state 0, you can never jump to state 1. And if you are at state 1, you can never jump to state 0. This so these submodels are not irreducible, and this has very nice properties that are very interesting, but I will not go into the details here. So now I jump to the results. First, as any scientific study, we begin with the simplest case, the equilibrium state. We emphasize that the equilibrium is defined by imposing that all the currents are 0. If you do this mathematically, you can prove that in order to have our model in the equilibrium state, it must satisfy this restriction on the parameters, where we have defined the reduced parameter as this fraction. In the symmetric case, this reads in this manner, equal to 1. We were able to, using this result from stochastic processes, to compute the actual probability distribution, for which I emphasize again, we are setting this condition, which is given by the equilibrium condition. And using this formula with the global rates, doing the product, you can find a binomial distribution, which behaves like this. But there is not much more interesting to say about the equilibrium state, so I will not waste more time here. And then we jump to the stationary states, which are usually more interesting. We managed to find the analytical solutions for Q from 1 to 4 using Mathematica, but they were so intrinsically complex, written in terms of Pohammer symbols and hypergeometric functions, that they were of very little use. So we focused on the numerical approach, for which we can find the probability distribution for any value of the parameters. And in particular, we focus on the symmetric case because I did some simulation. It was interesting, the general case. There are some non-trivial behaviors. But here we focus on the simple because we're doing some exploratory analysis and we want our life to be easy. So here, if you plot the stationary distribution, you can observe a transition from unimodal to bimodal for all, always for Q greater than 1. If Q is equal to 1, we don't have this transition. So the next question that we wonder is, when does this transition happen? For this, we do some mean field theory analysis. So as you know, mean field theories become better as you increase the number of neighbors because you are averaging over them. And since we are considering an all-to-all interaction, it becomes better as we increase n. We tested here for n equal to 50, and it was already pretty good. Below the critical point, I plotted 100 trajectories, and you have a very nice estimate of the average behavior. And I did the plot also above the critical point where you have this. Now, in the stationary state, which is where we care about, this term fades away, and we get a polynomial of degree q plus 1, which is equal to 0. So we have to find the roots. And below the critical point, we have one root, which is this one. And above, for all values of q, we always find only 3 real solutions, which are the 2 over there and one unstable one, which is also this one. So we can use this condition to find the critical point, and we find this critical value. Already from this expression, you can see how for q equal to 1, we have no phase transition, which is what we said before. And also interestingly, as you increase q, the transition occurs earlier, okay, which is also consistent with other models in the literature. We acknowledge that our model, well, in the rates, you can see that the set 2 symmetry is satisfied. So our model belongs to the Ising universality class. Therefore, it will inherit many properties of the critical phenomena. We calculated analytically the value of the magnetization. We plotted here. The mean field solutions are the dashed dotted lines, and the dots are the simulations. We see perfect agreement for several values of q. From this expression, we can see that the beta exponent is 1/2, as we would expect. And also, I want to note something that we will discuss later in more detail, that as you increase q, there is a big difference, because for q equal 2 to q equal 3, there is a big jump. But for q equal 4 to q equal 5, they are very near to each other. So the dynamics is more similar as you increase in q. So let us jump now to the main part of this thesis, which is the stochastic thermodynamics analysis. First, we focus on the macroscopic description or the ensemble description, and we start with the currents. The currents measure somehow the imbalance in the jumps of the process. For example, if it's very positive, let's say J1, you have that the Herding is beating the idiosyncratic behavior. So this would be a very positive current. We focus on the stationary state, for which by definition you get this condition. And we managed to obtain an analytical expression for the actual current, which also serves us was useful to prove that this was indeed the case in the stationary case. We will focus on intensive quantities. All the quantities that I'm going to present are extensive. So for the plots, I will always divide them by n. And now we explore the q dependencies of the current. So first of all, using the analytical expression, one can prove that the equilibrium value is indeed 0. And also you can see that it is always, sorry. And in the plot, well, the mean field lines are the dashed dotted, and they agree perfectly with the numerical ones. So we're happy with that. And the equilibrium is all the time 0, as you can see, as we might expect. And for the parameters higher than the equilibrium, we have positive currents, and below, negative currents. But more interestingly, theoretically, we can prove that in the limit of q going to infinite, the current goes to 0. But in the numerical analysis, we observe that already for q equals 7, we have already seen convergence, which is actually pretty interesting. Then we can do the analysis in terms of the h parameter, and we observe that there is the following behavior. We begin at a minima given by this analytical expression, and then it grows until a maxima at the critical point, which is given by this, and then it decreases to 0 as we go to infinite. Why a maxima at the critical point? Well, as you increase the parameter h, the jumps, the velocity of the jumps increases, but what happens is that you reach the critical point as suddenly the population splits in consensus, so you have less agents to interact with, and therefore you get a sublinear decay. That's the reason why. Now we consider the frenesy, which is the symmetrized version of the currents. This measures gives a measure of the jumps that there are on the system. we focus on the stationary state. In the mean field limit and the thermodynamic limit, we get this expression. And again, we observe from this expression that it is always positive, as one might expect. And we observe that the equilibrium value in this case decays like to the 2 to the q, 2 minus q, as we can see here. Moreover, we find also that in the limit going q to infinite, this goes to 0, but the convergence here is later for greater q's, which makes sense because in the frenesí, what we're measuring are the average jumps. So it has a higher dependence than the imbalance between jumps, as we discussed in the currents. Then for the dependence on h, we see that there is a minimum value given by this analytical expression. Then it grows until an inflection point at the critical point. And it is an inflection point also. The change in the curvature is also due to the fact that we reach consensus as we are in the at the critical point. Now we can consider the entropy, which is a measure of the uncertainty about our system. Obviously, as we increase n, the distribution becomes sharper. Therefore, the uncertainty decreases. If we study the analysis as a function of q, we observe for the equilibrium state q independence, which is consistent with the fact that our probability distribution was independent of q. And then for greater values, we observe the critical phenomena, which is more clearly in this plot as a function of h, which is obvious because when the phase transition happens, the peak of the distribution flattens, and this makes the variance increase. Therefore, we have more uncertainty. Wait. Okay. Now, I've been avoiding to do theoretical stuff so far, but I cannot go further without introducing the most important concept in stochastic thermodynamics, which is entropy production. It's defined in this way, and is a measure of the reversibility of the system, and is defined by an entropy flux, which is the reversibility given by the reservoirs, and then the change in entropy of the system. But in particular, we will be interested on the entropy production rate, which is given, which only focusing on this expression. Now you will see why. Okay, don't look at the other ones. And the affinities are these i's, which are given by this expression. Okay. Okay. Also, I want to define the coarse-grained entropy production, which is simply the entropy production, but without the sum over. So you don't separate the rates. You consider the global rate that you would use in the stochastic process usual analysis. And it can be shown using the Jensen inequality that the coarse-grained entropy production is always an underestimate of the actual entropy production rate. In the stationary state, obviously the distribution is static in time, therefore the derivative of the entropy is 0. This implies that the entropy production and the entropy flow are the same. Therefore, we will focus on the entropy flow, which has a nicer expression in terms of the affinities. That's why I told you only focus on this expression. For our model, the affinities have this nice expression, which is a term which we call the transient term that has an n dependence, and a biased term which only depends on the parameters. With this, we can find the analytical solution for the entropy production rate, which is the current multiplied by a bias factor, which is given by the parameters. Now, with these formulas, we know that this is a measurement of the irreversibility. Obviously, since the dependence of Q is only on J, we don't do this analysis here. So we focus on the H analysis dependence. Because of the logarithm, we have a divergence at the origin here. And also then goes to a null value at equilibrium, as we would expect. Equilibrium points should be reversible. Then we go into an inflection point at this value. Then, which is consistent with the previous literature. They also found that for some opinion models, there is some kind of inflection point here. And then it decays to 0 as h goes to infinity. So one question is why it diverges at 0 and why it goes to 0 at infinity. So at 0, you only have the idiosyncratic mechanism, which is a highly reversible mechanism, and you don't have the Herding mechanism. That's why it diverges. But as you go to infinite, the system reaches full consensus, and therefore it gets stuck there, and it cannot generate more entropy production. Therefore, you get 0. And finally, I want to emphasize that in the previous literature, they assessed that systems that satisfy global detail balance cannot produce irreversibility. And here we provide an example that does satisfy this, and we observe that indeed this is not 0. The problem was that they were actually measuring the coarse-grained entropy production. They did not separate the rates. Now, a little bit more of theory. So now here we present the most important equation of the whole stochastic thermodynamics, which is so beautiful because it gives us a proper intuition of why this is measuring irreversibility. On top, we have the probability of a stochastic realization of a trajectory, where a trajectory is defined simply by the points in which it jumps. And below, we have the probability of observing the backward trajectory, also reversing the thermodynamic process and the forces. In this way, what we're measuring here is simply the fraction of the probability of finding the forward and the probability of finding the backward. So it is a clear measure of the irreversibility of the trajectories. This can be written in this form in terms of a change in stochastic entropy and a stochastic entropy flux. And we note that if you do the average over many, well, in fact, all of the trajectories doing this path integral, you obtain the same ensemble quantities that we were discussing previously. And now the most important theorems of all the stochastic thermodynamics theory, which are the fluctuation theorems. The detailed fluctuation theorem states how likely it is to find the backward process, the backward trajectory. And we see that it is an exponential suppression. So this gives us a very good intuition of about the second law of thermodynamics. And the integral fluctuation theorem is also a consequence of this theorem, and it has this nice expression which serves as a good check for our simulations. Here I show again the affinities, and with these affinities we can find the analytical expression for the stochastic entropy flux, which is given by this term. And this is in fact novel to the literature because it was never found a term that was dependent. This transient term was never found previously, so we're very happy with that. And okay, yeah. So now we analyze, of course, in the ensemble limit, when we do the averages, this term must vanish, as we already saw that the entropy flux was only given by this term. So on average, this term has to vanish. We can do these plots, and we see that indeed, as we increase the number of trajectories over which we average, this term vanishes. And then we have an idea of something that could be very interesting. And it can be shown that as you do longer and longer trajectories, the change in entropy goes to 0, but we are not sure still if the transient term also goes to 0. If it went to 0, we could use this version of the fluctuation theorem, which would allow us to find experimentally on a lab what are the actual rates of the transitions, which would be very, very interesting. But for this, we need more time because we would need to do a proper analysis using full counting statistics. Then we assess the fluctuation theorems because they serve as an additional check to our methods and provide lots of insight. Already in the literature, they have emphasized how hard it is to test them, both experimentally and on simulations. Why so hard? This is because of the exponential suppression that I was mentioning on the detailed fluctuation theorem, which makes it very difficult to get enough statistics. And to give an intuitive idea, this is because the more complicated trajectories you have, the harder it will be to find them, and the harder exponentially will be to find the backward ones. Therefore, in terms of our model, for example, as you increase the length of the trajectories with the time, there are more jumps, and it will be more difficult to find the inverse. We do this analysis for all the parameters. Let's start from right to left. We see as we increase n, the integral fluctuation theorem gets worse and worse. But still, we managed to get some good results until 200. There's only one paper in which they tried this, and they only did for 16, I think. Then we analyze how it changes as we increase the length of the trajectories, and we observe how disaster it becomes as we increase it. And finally, we analyze the dependence on the rates, which account for the jumping velocity. So here there's something very interesting, that at the critical value, which was equal to 3, we have found that something happens, right? Therefore, I checked also the fluctuation theorem, which the fit is perfect. It has to have a slope of 1, and we get a very good agreement. And to understand more this critical phenomena that I was talking about, we analyzed the probability distribution of the entropy production before and above the critical point, and we found that indeed there is some fat tailness after the critical point, which seems interesting. But in order to do a concluding analysis, we should use techniques of large deviation theory, which we didn't have enough time to implement. So to conclude, we have managed to apply stochastic thermodynamics without the need of any thermodynamical interpretation. We have learned how to properly differentiate the equilibrium versus the stationary states, finding that we need to find the equilibrium condition which characterizes them. We introduced new measures to the game. So with these measures from stochastic thermodynamics, we can gain more insight about the phenomena. And also, apart from the fluctuation theorems, there are many more relationships that can be used and can help us to find more interesting results. In particular, we have fully characterized the equilibrium state because we have found the probability distribution. And as we know, a stochastic process is characterized by the probability distribution. Secondly, we have done a deep analysis of the stationary states. Then we have done the ensemble stochastic thermodynamic analysis, showing that the critical point shows certain hallmarks on the measures. And finally, we have done the path analysis, in which we have found a new transient term that was not previously known in the literature. And as future directions, we could answer the remaining questions that we left by doing a proper mathematical analysis. We could also consider the study of small systems, because a thing that I didn't emphasize is that stochastic thermodynamics provides a fluctuation analysis, and this is interesting for small systems, which we could analyze. We could consider the general case of all of the parameters, embed the model on a network, not all-to-all interaction, could be interesting, and consider other mechanisms like annihilation or creation, or extend this framework to other models that are not so well fitted for the stochastic thermodynamics approach. Thank you.